Hello everyone, welcome back. In this lesson, we're going to look at finding a pool t interval for comparing the difference between two population means. And recall that for finding a pool t interval or a pool t test, we assume that the population variances are the same. Okay, so we have this extra assumption where we have equal variances, and recall that we found the pooled standard error by using the following equation. Okay, so to find the pooled standard error, we first find a pooled standard deviation, which is SP, and then we multiply this by the square root of 1 over the sample sizes. And the pooled variance is calculated by taking this weighted average formula of the two sample variances. Okay, so we use a student's t distribution for the sampling distribution model, and where the degrees of freedom are n1 plus n2 minus 2. So we're going to look at finding a confidence interval. So recall that for a confidence interval, we look at the estimate, which will be the difference between the two sample means, so y1 bar minus y2 bar. We add and subtract a critical value times the pooled standard error. And recall that the critical value is going to depend on the level of confidence and the number of degrees of freedom. All right, so let's have a look at the example here. So we have the feeding habits of two species of net casting spiders are studied. The species Dinopus and Menaeus coexist in eastern Australia. So the following data were obtained on the size in millimeters of the prey of random samples of two species. So here we have sample data of the size of the prey. And we have the following summary statistics. Okay, so we have the average size for Dinopus, which is 10.26 millimeters, with a standard deviation of 2.514. And for Menaeus, we have an average of 9.02 with a standard deviation of 1.897. So what is the difference, if any, in the mean size of the prey for the two species, assuming the underlying populations are approximately normally distributed using a 95% confidence interval? Okay, so the first thing we'll look at is the assumptions and conditions. So we have independent responses. All right, so we're looking at the sizes of prey from both species. So within each species, the size of prey of one spider should not affect the size of prey of other spiders. Okay, so they are independent of one another. And because we are dealing with multiple groups, we have the independent groups assumption. So the size of prey of one species should not affect the size of prey of other species. So now to check for independence, we look for randomization. And we're given that we have random samples of the two species. Okay, so we have random samples, therefore our randomization condition is met, so we can assume independence. Now the other assumption is that the populations should be normally distributed. And here we are assuming that the underlying populations are approximately normal. Okay, so we assume the underlying populations are approximately normally distributed. Oops. There we go. So this is important because our sample sizes are smaller than 30. And so we do need to have that the populations are normal. Okay. So now the next thing is to check whether or not we can assume equal variances. Okay, so now this will decide whether we should be using a pool t-test or a two-sample t-test. Okay, so now let's check for equal variances. And recall to check equal variances, we will look at the ratio of the two standard deviations. So we're going to look at finding the larger standard deviation divided by the smaller standard deviation. Okay, so we have 2.514 and 1.897. So if we take the ratio of these two standard deviations, we end up with 1.325. And because this ratio is smaller than 2, we can assume equal variances. And then we'll proceed with a pool t-test. Now, if the ratio was larger than 2, then we should be using the two-sample t-test instead. Okay, now because the ratio is smaller than 2, we will be using a pool t-test. Sorry, a pool t-interval, not a pool t-test. So now let's have a look at finding our confidence interval. So here we want to look at the difference between the means. So we can look at finding the difference between Danaus and Minopus. Now it doesn't matter which difference we define it as. We can find the difference between Menaeus and Dinopus, or from Dinopus and Menaeus. The only difference in the end is interpreting the confidence interval. Okay, then we add and subtract a critical value. Then we multiply this by a pooled standard error. Okay, so now let's look for our critical value. So we need to determine the degrees of freedom. And for a pool t interval, the degrees of freedom are the sum of the sample sizes minus 2. Okay, so now if we look in our data, we have 10 values for both groups. And so we have sample sizes of 10. And so our degrees of freedom is 10 plus 10 minus 2, giving us 18 degrees of freedom. So now we can use our t-table to determine our critical value. Now we want to look for a 95% confidence interval. So for 95% confidence and 18 degrees of freedom, the critical value is 2.101. And that is for 95% confidence. All right. So now the last thing we need is the pooled standard error. And to find the pooled standard error, we first need to determine the pooled variance. Okay, remember that pooled variance is SP squared and was given by that weighted average formula. So we have ND minus 1 times SD squared plus NM minus 1 times SM squared, and that's all over the degrees of freedom. Okay, so our sample sizes are 10, so what we have is 10 minus 1. The standard deviation for Dinopus was 2.514. So we square that, then we add it to 10 minus 1. And then the standard deviation for Menaeus is 1.897 squared. We divide all of that by 10 plus 10 minus 2. Okay, so our pooled variance is 4.9594. So now we will calculate the pooled standard deviation by taking the square root of the pooled variance. Okay, so the square root of 4.9594 will give us a pooled standard deviation of 2.269. And now we can use this to calculate our pooled standard error. Okay, so we calculate the pooled standard error by taking the pooled standard deviation, so that's 2.2269, and then we multiply this by 1 over 10 plus 1 over 10. Then our standard error is going to be 0.9959. All right, so now we're ready to find our confidence interval. So we're going to subtract the means of the species. So we have 10.26 minus 9.02 plus or minus 2.101 times 0.9959. And so we get 1.24 plus or minus a margin of error of 2.0924. And so our confidence interval is from negative 0.852 and positive 3.332. Okay, so what we can say is that we are 95% confident, that the true mean difference between the size of prey of the two species is between negative 0.852 millimeters and positive 3.332 millimeters. Okay. Now notice that our interval contains 0. Okay, so because our interval contains 0, then we cannot conclude that there is a difference between the size of prey right? If we wanted to conclude that there was a difference between the size of prey, then either the confidence interval is entirely negative or the confidence interval would be entirely positive. Okay, so if the interval was entirely positive, this would tell us that the size of prey for Dinopus would be larger than Menaeus, and if the interval was entirely negative, then it would be the other way around. So the size of prey for Menaeus would be larger than Dinopus.